Example 4. It says to create a table values of 2 to the x and 1/2 to the x on the same axis. What do you notice about them? We kind of did that up here. We kind of did that right here. What did we say about 2 to the x and 1/2 to the x? How are they related to each other graphically? If they're reflections of each other across the y-axis. Yeah, there you go. If one of them is increasing by doubling and the other one is decreasing by halving, then they're really the same growth rate. They're just on opposite sides of the y-axis. So we could actually do the same thing for e and 1 over e. We could do the same thing for 3 and 1 over 3. So here's what we need to know from this. Reciprocal bases, or let's just do this, exponential functions. This is what we need to know from this section. Exponential functions with reciprocal bases have graphs that are reflections across the y-axis from each other. There we go. Reciprocal bases are reflections across the y-axis from each other. Now you could see that clearly in this little diagram right here. If you notice 2 to the x, and if you reflect it across the y-axis, you get 1/2 to the x. If you see 3 to the x and you reflect it across, you get 1/3 to the x. 5 to the x becomes 1/5 to the x. 10 to the x becomes 1/10 to the x. Okay, now we can come up with some kind of standard for the steepness of the graph. Let's look at exponential growth. These are all exponential growth. We could say this. For growth, the blanker the base, the steeper the graph. What can we put in the blank? The greater, yeah, the greater the base. The greater the base, the steeper the graph. Something that doubles every cycle versus something that triples every cycle versus something that quintuples or increases by a factor of 10. The bigger the base, the greater the scale factor is, and so the faster it's going to grow for large values of x. So it makes the graph steeper. Now, not only does that mean that it goes to infinity faster on the right-hand side, but notice the purple graph over here. The purple graph is also going to the x-axis faster. See that? They intersected 0, 1. They all intersected 0, 1. But not only does it go to infinity faster, but it also goes to 0 faster on the other side. It gets smaller faster, 1 over 10, 1 over 100, so on and so forth. Now, for decay, for the left side here, let's see if we can come up with something. For decay, which is decreasing functions, the blanker the base, the steeper the graph. Bless you. Bless you. What's the steepest one on the left-hand side? 1/2 or 1/10? 1/10, okay, which is steeper than 1/5, which is steeper than 1/3, which is steeper than a half. So what's happening to the bases as they get steeper? Are they getting bigger or smaller? Smaller. So for decay, the smaller the base, the steeper the graph. Okay, we always want to be able to compare one growth function to another growth function, or one decay function to another decay function, to see which one is steeper. Okay, so let's answer this question. Let's put this example in here. Let's call this example 4B. You're going to see questions like this on your homework. It's going to say solve, and we're going to do 4 to the x is greater than 5 to the x. Solve. 4 to the x is greater than 5 to the x. What the heck is that asking? That's asking for what values of x are the y values on the left bigger than the y values on the right. So guess how we're going to solve this one? We're going to do a quick sketch. Now, what do both of these functions have in common? These are both exponential functions. What graphical features do they share? They're both monotonic increasing. Good. They're both growth. What's their y-intercept, both of them? 0, 1. They both pass through 0, 1. And what's their left end behavior? As both of them go to negative infinity, what are they approaching? They're approaching 0. So what graphical feature does it have? There's a horizontal asymptote. So those are the two things that I'm looking for. They have common features of y-intercepts and a horizontal asymptote at 0. Now, let's pick a flavor. I'm going to graph 4 to the x in this green color right here. So I'm just going to draw an exponential growth function that looks like that. All right, now I'm going to pick red for the next one. And I just have to now draw it either steeper or less steep than 4 to the x. Well, is 5 to the x steeper or less steep than 4 to the x? Steeper, right? So right here to the right of 0, it's going to be above like that. And to the left of the 0, it's going to be underneath it like that. And now that I have them both drawn, I can answer the questions. For what value of x now is the green graph above the red graph? That's another way to interpret that question. For what values of x is the green graph greater than or above the red graph? And of course the answer is what? For all x, not 0 to negative infinity, but negative infinity to 0. Right. Or you could just say for x less than 0. Yeah. Very good. To the left of 0. They intersected 0, 1, so that's what they changed. So the answer was either going to be to the left of 0 or to the right of 0. We just had to know where they fell in relation to each other. Got it? So y'all can answer questions like that now, right? Piece of cake. All right. Example 5. Graph the parent function. Okay, so e to the x. Y'all remember what e is approximately? 2.718. So 2.7. If you remember it's 2.7, that's good. E to the x would fall somewhere in between these two right here. If you want to look at y equals e to the x, it would fall somewhere in between there. But it's going to become our parent function. So let's go ahead and draw it once by itself. And we'll start talking about some of its features. First of all, we'll get the common feature down. It has a horizontal asymptote at y equals 0. It has a y-intercept of what? 0, 1. Yeah, a y-intercept of the ordered pair is 0, 1. And it's monotonic increasing, so it looks something like this. Now, unless we put another exponential growth function on the same graph, we don't need to worry about how steep we draw it. Would y'all agree? If it's just an exponential growth function, we'll just draw it like that. Okay, let's find the characteristics then above. The domain. What's the domain of this function f? All real numbers. Is that the domain of all exponentials? Yes, that's true. Okay, what's the range of this function? Greater than 0. So you say the set of all y such that y is greater than 0? Or you could say y epsilon 0 with the parenthesis to infinity. Either one. Is e to any number ever going to equal 0? No. Is e to any number ever going to be negative? No. Same thing with 2, right? 2 to any power is never 0. 2 to any power is never negative. These characteristics for the domain and range are true for all exponential growth and decay functions of the form b to the x. Okay, we already found the y-intercept. Are there any x-intercepts? No. So I'll just come over here and put none for x-intercepts. Any symmetry? No symmetry. Good. There's no y-axis symmetry. There's no origin symmetry. Intervals of increasing or decreasing. I'm going to say that this one is monotonic or strictly, that's the other word we use, monotonic or strictly increasing for all x. That means over its entire domain of all real numbers. And then the end behavior. Let's go ahead and write that off to the side here. That's pretty important. The limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. I'll write it like this. What would be the right end behavior? Infinity. Okay? So as x goes to infinity, so do the y values. What would be the limit as x goes to negative infinity? 0. And that's why there's a horizontal asymptote at y equals 0. This is perhaps, or these, I should say, these end behaviors are perhaps a pair of the most important characteristics of all exponential functions, whether they're growth or decay. They have very dramatically different end behaviors. On one hand, they go to infinity or negative infinity if we mess around with them. And on the other hand, they approach some finite value like 0. Right? Very dramatically different end behaviors. All right, is there anything else you want to say about e to the x before we move on? That's your parent function. It's your parent function. This Corby. Yes, we'll send him. Wyatt, you're going down to student services. Yeah. Take your stuff with you. Who knows how long you'll be gone. All right.
This video is going to be on Corby's World.
Yeah, I will. Yeah, and your name is, we're saying your name. Bye, Wyatt. Okay. Hey, so guess what? Just like with all the other functions that we've had, now that we know what the parent function looks like, we can start graphing transformations of the parent function. Okay, so let's look at example 6. Sketch f of x equals 3 minus e to the x minus 1. Well, let's recall what standard transformation form looks like. It's a times f of b times x minus c closed plus d. This is in general. For exponentials, it's going to be, we can make it more specific. It's a times e to the bx minus c plus d. So let's quickly review this. What does it mean to be inside the exponential function? Where is it going to live? Well, what part of the equation? If you're inside the exponential function, you're affecting the x values. That's your b or c. They take place in the exponent. That's what I'm looking for. They take place in the exponent. That's what you meant. And if it's affecting the y values, it's on the outside of the exponential function. It's on the ground level. It's either the a value in front or it's the plus d that we're adding down at the bottom. Okay? So let's go ahead and put this one into standard transformation form because it's currently not. I get f of x equals negative e to the x minus 1 and then plus 3 at the back end. All right, let's go ahead and come off to the side and list the sequence of transformations just so that we make sure we know what's happening here. What is the negative in front going to do to this function as it would to any other function? X-axis. So to use fewer words, we'll just say x-axis reflection. X-axis reflection. What would the minus 1 do? Right 1. Good. And then the plus 3 would be up 3. Good. Now let's see what happens. Let's go ahead and sketch ourselves a little e to the x graph here so we can kind of imagine what's happening. So let's say that this is your parent function e to the x. And let's go ahead and do the sequence. Let's go ahead and reflect it across the x-axis. The x-axis is where the 0 was, right? That's the horizontal asymptote. So reflecting it across the x-axis is the same as reflecting it across the asymptote. So now it's going to live down here. It's going to look like that. So that's going to be negative e to the x. Y equals negative e to the x. All right, now let's pick it up and move it right 1. If I pick it up and move it right 1 unit, does that really do anything significant to it? No, it has the same shape, doesn't it? If I pick that graph and move it right 1, it's still decreasing below the horizontal asymptote. That doesn't affect it that much. But look at the next one. Oh boy. This Scorpy. Yeah. Simmons. Yes, I'll send him down too. Okay. Student services. Take your stuff with you. It's busy down there this morning. What does the plus 3 do to this graph? Up 3. Now, when it moves it up 3, what's going to happen to the horizontal asymptote? It's going to go up 3 as well. That's a significant change, right? So when we're sketching our final graph, let's come down here and sketch our final graph. Good luck, Ryan. We get our final shape when we're done with the reflection. The reflection is the only thing that is your A or B value. Remember, A or B reflect or change the shape or the orientation. In this case, it opens down. The C and D only affect the location. So the location is going to be moved. So even though it's the last thing that we do, moving it up 3, it's the first thing that we draw when we're sketching our graph. We always draw the asymptote first. And now all I have to do is draw it decreasing below the horizontal asymptote. Now, there's one last thing that we need to make sure we get correct. Notice I have mine crossing the y-axis in positive land. If I pick this graph up and I move it right enough or left enough, notice if I move it left, it changes the y-intercept, doesn't it? If I move it left enough, it's a negative. If I move it left enough, it could be passing right through the origin. And if I move it not left enough, it's still positive. Let's go ahead and find the y-intercept. That's what we did in the past. So for the y-intercept, I'll come off to the side here, and I'm going to plug it into the original version, this guy right here, because the other version is easy for graphing. The original version is easy for evaluating. So let me do f of 0. It's 3 minus e to the negative first power. Well, that's the same as 3 minus 1 over e. Is that going to be positive or negative? That's positive, right? That's like 3 minus a third-ish. 3 minus a third. All I need to know is that that's positive. So I'm going to put greater than 0. So is my graph that I have drawn okay? It is. Yeah, I'm not going to measure it to make sure it's at 2 2/3. I'm just going to say, oh, it's positive. That's good. I'll put arrows on the end. Maybe I'll put a little dot there to show that it does cross. And there it is. There's your answer. Okay. Now let's go ahead and talk about a couple things here. Domain. What's the domain of this function? All real numbers, right? That doesn't change at all, ever. But the range changed here, didn't it? It's no longer everything above the asymptote. It's everything below the asymptote. Oh, and by the way, we moved the asymptote. So it's the set of all y such that y is what in relation to 3? Less than 3. Okay, you could do it like that. Or you could say y epsilon negative infinity up to 3 close parenthesis. Either way. All right, we got 2 end behaviors to figure out. What's the limit as x goes to infinity of f of x? And what's the limit as x goes to negative infinity of f of x? Let's do the right end behavior first. Hop on the graph, head out to the right. What does it go to? It goes down to negative infinity. Very good. And what's the limit as x goes to negative infinity? It's going to 3. Yeah. Now, let's see. We could get that from the graph. Is there a way to pick up the end behaviors from the equation? Let's come over here and see. If I plugged in, this is off to the side. This is my workbench. We don't consider this actual real work. But if I just say f of infinity, that doesn't really make sense, does it? F of infinity. I can't plug infinity in as a number, but I'm just going to take some, what's the word I'm looking for? I'm going to plug in infinity. I'm going to take some license here. Oh, he left his drink. If I plug in infinity, let's see what happens. I get 3 minus e to the infinity minus 1. What's infinity minus 1? Should be infinity, right? Infinity minus 1 is still infinity. Would you agree? Yeah? And now what's e to the infinity power? It should be infinity. E to the infinite power should be infinity, right? So now I get 3 minus infinity. What's 3 minus infinity? Negative infinity. Is that what we got for our right-hand behavior? Yeah. So we can't plug in infinity per se, but I can plug it in mentally and just think of it as a limit, right? When I say f of infinity, I really mean the limit as x goes to infinity. Okay, let's see what happens if I do the other one. What would be f of negative infinity? Well, if I plug it in, I get 3 minus e to the negative infinity minus 1. Let's evaluate it from the top down. What's negative infinity minus 1? Negative infinity. Yeah, good. Now that's the same as 3 minus 1 over e to the positive infinity. When you have e to the negative infinity, that's the same as 1 over e to the positive infinity. Well, what's e to the positive infinity? In the bottom. What's e to the infinity? Infinity. Now look what we have here. What is 1 over infinity approaching? 1 over 10, 1 over 100, 1 over a million, 1 over a zillion. That's getting closer and closer to 0. And now what's 3 minus 0? 3. Is that what we got when we went on the graph? Yes. So that's what's kind of cool about exponentials and end behavior. You can't plug in infinity and negative infinity per se, but we can think about what happens to the function as we get larger and larger and larger x values. And we can get the two end behavior limits analytically and not just from the graph. But we do end up with the same answers, which is what we would expect, right? That's how math works. You get the same answers. If you're doing it right, you can do it a couple of different ways, get the same answer. All right, any questions on that one? All right, let's jump to example 7. Sketch this dude. Give the domain and range, find the exact value of the y-intercept. Okay, now notice this one is exponential. I can see it's exponential. I have a variable in the exponent, and I have a numeric base. What's the parent function here? 7 to the x, right. The parent function here is y equals 7 to the x. Is that growth or decay? It's still growth, yes? So for all practical purposes, I can say my starting graph looks pretty much the exact same as e to the x, doesn't it? It's going to pass through 0, 1, and it has a horizontal asymptote. It's just going to be a little bit wider than e to the x. Steeper. It'll be a little bit steeper than e to the x. But again, if I'm not graphing another function on the same grid, I can just say that's the basic shape. It's monotonic increasing. Okay, now let's put our equation in standard transformation form, because I don't think it is. The negative 3 is going to be in the front, times 7 to the. In the exponent, I got to put the x first, so it's negative x plus 5, and then the plus 4 goes back down on the ground level, on the back. Is that standard transformation form? Good. No, not quite. There's still something left to do on the inside in the exponent. Not only does the x term have to be first, but the coefficient of the x has to be a 1. So in the exponent, I have to factor out the negative, and I get x what? Minus 5, close parentheses, and then plus 4. All right, let's come off to the side and describe the sequence. Here's what's happening. What does the negative in front of this equation do? X-axis reflection. X-axis reflect. Good. And the 3 itself does what? Vertical stretch by a factor of 3, right? The same things that we did with the other functions earlier in the year. The 7 is the base. What's the negative in front of the x do? Y-axis reflection. Good. Y-axis reflection. And then very similar like in the previous problem, the minus 5 will move it right 5. And then the plus 4, the fifth and final transformation, the plus 4 moves it up 4. Okay. Now the most important transformations here are the reflections and the vertical shift. The reflections are important because they change the orientation. Lane, your earbud needs to be out. You know that. I shouldn't have to tell you that here into the 9 weeks period. The reflections are important because they change the orientation, right? And then the vertical shift is also important because that changes the location of the horizontal asymptote. So let's think about what that's going to look like. The x-axis reflection is going to take 7 to the x, and it's going to make it look like that. Now if I take that red graph and I reflect it across the y-axis, it's going to make it look like this. So that one right there that I'm highlighting, that's your final shape. That's important. Your final shape is increasing below the horizontal asymptote. Increasing below the horizontal asymptote. Increasing below the horizontal asymptote. And where's the horizontal asymptote located? Up 4. Oh my gosh. Is this Corpy again? Guess what? Okay. We get rid of them all here. Oh, Kenna is testing in TSI this morning. Yeah. Yeah. Up 4. So that means that there's a horizontal asymptote at y equals 4. Okay, so we're ready to sketch our final graph here. We draw our x and y axis. We come up here to 4, where the horizontal asymptote is. We draw the horizontal asymptote, And then we know it's decreasing or increasing below, increasing below, increasing below. So it looks something like that. Now, again, depending on whether I shift it left or right, I could have a positive y-intercept, a 0 y-intercept, or a negative y-intercept. I did shift it right 5. So right 5 might actually take this from a positive y-intercept to a negative y-intercept. How can I figure it out? I find it, right? So I'm going to come back up here to the original version, and I'm going to plug in a 0 for x. So I get f of 0 equals 4 minus 3 times 7 to the 5 minus 0, which is to the 5th power. Now let's see if that's positive or negative. That's going to be 4 minus 3 times. What's 7 to the 5th? It's a big number. It's a big positive number, right? What's 3 times a big number? A bigger number. So what's 4 minus a bigger number? Is it positive or negative? It should be negative, right? Like 4 minus 100, let's say.
But it says 4 minus a bigger number.
Yeah, so let's try it out. So for an example, what would 4 minus 100 be? It would be negative 96. Yeah, so 4 minus a bigger number is going to be less than 0. So my y-intercept should be negative, right? And the way I have it drawn right now, my y-intercept is positive. So when I shifted it right 5 units, it was substantial enough to make it cross the negative land. So just redraw it or pick up your graph if you're doing it in Notability and just scooch it over. Okay? So we always want to be mindful of that y-intercept. I don't really need to know the decimal value. The exact value is fine. 4 minus 3 times 7 to the 5th. It's a negative number. Okay, let's talk about some stuff on them now. The domain. What's the domain of this function? We did that with our eyes closed, didn't we? All real numbers all day long. The range of this function. Anything less than 4. So we say the set of all y's such that y is less than 4. And the two end behaviors. What's the limit as x goes to infinity? 4. Good. And what's the limit as x goes to negative infinity? Negative infinity. If you trust that your graph is right, it's real easy to get those limits from the graph. If you don't trust that your graph is right, you could plug infinity in for x and find it analytically like we did on the previous problem. I'm not going to go ahead and do that. All right, any questions on example 7? I'm going to take another 10 seconds to see if the phone might ring again. That was a record. At least they gave us the new phones, which are now on my desk. It used to have to be plugged in over there by the door, and every time the phone rang, I'd have to go way over there to answer it. Now,
But the dial tone tell the ringtone.
yeah, you're right. Yeah. Okay. Let's go ahead and we did this earlier in the year, finding equivalent transformations for exponential functions. We did it for all kinds of functions. We did it for radical functions. We did it for many, but now we're going to do it we'll do it again. The following transformation of an exponential function can be achieved in more than one way. For each of the following, describe 2 different ways to achieve the graph, okay? 2 different ways to achieve the graph. So we are reviewing here a little bit. Let's say I start with x squared, and I'm ending with 4x quantity squared. What's the first way that I can get from x squared to 4x quantity squared? In other words, what would this 4 do? Well, is it a vertical stretch or a horizontal compression, or what is it? If it's inside, this is a b value, right? So it's a horizontal compression. Good. It's the opposite of what it appears. It's not 4 times wider. It's 4 times narrower. It's a horizontal compression by a factor of 4. We did this earlier in the year, if you recall, when we were studying things in chapter 2. Now, to get it into an equivalent version, I need to somehow manipulate the equation. So what can I do to 4x quantity squared? Well, that's 4x times 4x, isn't it? So that's the same as 4 squared x squared, which is the same as 16x squared. So what is this 16 now? It's your a value, and it also gives you then another way to obtain the same graph, which is to what? Instead of horizontally compressing it by a factor of 4, we can vertically stretch it by a factor of 16. Yeah, this is review. We've already done this year. We're just working up to exponentials. Okay, how about this one? to get from the square root of x to 4 square root of x? Well, let's do the first one first. This is an a value in front, so the obvious one would be a vertical stretch by a factor of 4. Okay, good. Now, the other version would be requiring me to get it on the inside. So if I want to get g of x equivalent, it would have to be some number on the inside. What number would that be? Would it be 2?
Yeah.
It would be 2. You think?
Wait, no, it'd be 16.
It would have to be something good. It would have to be something that when I took the square root of it would give me 4. So I'm not taking the square root of 4. I'm actually squaring 4 to get 16. Because the square root of 16 on the inside would give me the 4 on the outside. So now that turns it into a what? This is a b value again. Horizontal compression by a factor of 16. Okay, good. Remember doing this earlier in the year? Yes, piece of cake. It's just review. All right, now let's look at the exponentials here. This makes it more exciting. Okay, so for exponentials, let's look at the first one that we have right here. This -1, that's actually a c value. So it's going to be a horizontal what? Shift. So is it left one or right one, or it's right one? So I'm just going to say R1. Are you okay with that? R1. Now to get it into something equivalent, let me move this over so I can work straight down. To get it into something equivalent, here's what I need to do. I use this little property that says a to the, well, let's do this. X to the a minus b, or a plus b, is equal to x to the a times x to the b. That's the property that I just used. So 3 to the x minus 1 is 3 to the x times 3 to the negative 1. Now that's the same as 3 to the x times 1 over 3 to the positive first. And now I can bring the 1/3 out front and say it's 1/3 times 3 to the x. And that did the trick, right? Because now I took it from a c value to an a value. So what would be the other way to do it? Either shift 3 to the x right one, or vertical compression by a factor of 3. Very good. Vertical compression by a factor of 3. Vertical compression by a factor of 3. All right. Not bad for a free day on a Monday, huh? Not bad. All right, let's look at this one. We're starting with f of x, and we're trying to get to g to the x. Now, this one's interesting. We're trying to go from a base 3 to a base 9. Base 9 is going to be steeper, right? So I might have to stretch it somehow. Well, let's see what I'm going to do here. Let's see if we can think about this one graphically. If I have 3 to the x that looks like this, and I'm trying to get to 9 to the x, 9 to the x would look like this. Will a vertical stretch work?
No.
No. What happens to the y-intercept on 3 to the x if I stretched it vertically? It would change, wouldn't it? The y-intercept at 1 would move up. So instead of stretching it vertically, I'm going to have to get there by doing what? No, a shift would change the y-intercept too. I would need to compress it horizontally by some amount. A horizontal compression would keep the y-intercept intact. So here's what I'm going to do. I'm going to take g of x, and I'm going to write base 9 as a power of 3. What's another name for 9 in terms of 3? 3 squared. I'm going to write it as 3 squared. Now I'm going to use that property that says when you raise a power to a power, what do you do with the exponents? You multiply them, and I get 3 to the 2x. Well, that 2 right there now tells me to do what? That's a b value, so it's going to be a horizontal compression by a factor of 2. A horizontal compression by a factor of 2. Now, is there another way to get it? No, the only other way to get it is to graph it originally as a 9 to the x. So this one only has one equivalent way to do it. You either graph it as 9 to the x, that's the first way, which is steeper base, or you take 3 to the x and you horizontally compress it by a factor of 2. All right, what about this guy? I'm trying to get from 3 to the x now to 9 to the x plus 1. Well, we do the same little trick here. I take 9 and I replace it with 3 squared. And now I raise it to a power and I get 3 to the 2 times x plus 1. And now I can talk about what this one does, right? What does the 2 do?
Horizontal compression.
Horizontal compression by a factor of 2. I get that out of the way. And then, after that, what is the plus 1?
Right hook.
Move it
Or
left 1. Very good. It's the opposite, so it's left 1. Bless you. Bless you. Now watch, we can keep going with this. If I distributed the 2, I get 3 to the 2x plus 2. Yes, yes? And now I can use that property from above that says it's 3 to the 2x times 3 to the second, which now I could bring the 3 squared into the front and call it 9 times 3 to the 2x. So what's another way to manipulate 3 to the x? I could say, or, what would the 9 do? Vertical stretch by a factor of 9, and then follow that by a horizontal compression by a factor of 2. So this one does have 2 ways to do it. They're both in terms of base 3. Either horizontally compressed by a factor of 2 and then move it left 1, or vertically stretch it by a factor of 9 and then horizontally compress it by a factor of 2. So whenever you're manipulating these exponentials, it's important to know these following 2 ideas here. Let's write it again. X to the a plus b is x to the a times x to the b. That's the first one to know. And the other one, x to the a to the b power, is x to the a times b power. Those are the 2 important ones to know when you're manipulating exponential. All right. So far, so good? All right, let's do example 9 and we'll call it a day. I think we can figure this out. Now we're writing equations of exponential functions in the form b to the x. We're writing equations in the form b to the x whose graph is given. So all we're trying to do to write the equation is we want to find b. That's it. We need to find b. b is going to equal what? Well, because it's one unknown, we need 1 point. We need 1 point to find one unknown. And it can't be the y-intercept. The y-intercept we know is going to be 0, 1. So let's use this point, 225. So here's what we're going to do. We're going to say at the point 225, we plug in a 25 for f of x, and we plug in a 2 for x. This is your x, and this is your f of x. We just plug it into this template right here. Everyone see what I did? I just plugged it in. Okay, now all I got to do is solve for b. Yeah, you take the square root of both sides, and what do we have to remember to consider when we take the square root? Plus or minus the square root of 25. So that means b equals -5 or b equals +5. Those are the 2 solutions to the equation. But in the context of this problem, we're trying to find the base of an exponential function. Can we have a negative base? No. So we've considered it, but then we've thrown it out. So b is equal to 5. So this equation must be f of x equals 5 to the x. Now you probably could have looked at that and just said that right away. Probably realized, hey, 5 squared is 25. What would be this ordered pair at x equals 1? 1 comma 5, right? What would it be here at 0? 0 comma what? Not 2, but 1, right? 5 to the 0 is 1. So 5 to the 0 is 1, 5 to the first is 5, 5 to the second is 25, so on and so forth. What would it be right here at -1? What's 5 to the negative first? 1/5. So that's -1 comma 1/5. So on and so forth. Okay, good. So it works. All right, let's do 3 and 1/8. This one is going to be exponential decay. So we take our template, f of x equals b to the x, and we say at the point 3 comma 1/8, colon, that says that we're plugging it in. We get 1/8 for f of x. It equals b to the third. And now we take the cube root of both sides. When I take the cube root of a number, do I consider plus or minus? No. Now what's the cube root of 1/8? What number times itself 3 times? That's the same as the cube root of 1 over the cube root of 8, which is 1 over the cube root of 8, yeah. So b is equal to 1/2. So my equation must be f of x equals 1/2. We write the base in parentheses to the x power. Whenever your base is a number between 0 and 1 as a fraction, write it in parentheses. Okay, that's it. That's today's lesson. We got through example 9. We might be able to finish the notes tomorrow. I think we will. All right, so that's looking like your worksheet will be due when? Wednesday. All right. Have a good day. Don't forget to subscribe to Corpus World on YouTube and tell all your family and friends and neighbors about it.